Welcome back to the channel. In today's session, we will set up a single ADC channel and demonstrate how to make decisions based on the voltage level detected at the ADC pin. We will start with a quick recap of how ADC works and explore the different scanning mechanisms. Then we will move on to the implementation, walk through the code to understand the configuration, and finally wrap up with a live demo. The TC27X microcontroller comes with a set of analog input channels that are connected to a cluster of analog to digital converters. These converters uses the successive approximation register principle to convert analog inputs signal like voltages into descriptive digital that the controller can process. Each SIR converts in the TC27X also includes its own dedicated sample and hold unit for accurate measurement. The VADC model supports two types of channel scan sources. Group scan source. This can request conversion from all channels within a specific group. And the second one is the background scan source. This can request conversions from all channels across all group. It's important to note that priority channels which are defined in the group scan source cannot be part of the background scan sequence. Both scan sources works in the same way and share the same registers interface, but the background source offers more request and pending bits because it covers all groups. We quickly check some of the key feature of the VADC. It operates on a nominal analog supply of 5 volts and even with 3.3 volts also, but it slightly reduces the performance. Accepts an input voltage range from 0 volts up to the analog supply volt. It supports both standard V reference and alternative channel 0 reference voltage for flexible measurement, and includes up to 8 independent converters, each with up to 8 analog input channels. Offers external analog multiplexer control, adjust sample time and scan support, and it provides conversion time below 1 microsecond. Again, it depends on resolution and sample setting. Allows flexible source selection and sequencing, programmable single or repeat conversion sequence, automatic scanning for each conversion or across all converters in the background, converts trigger by software, timers or external event, even cancel the inject restart mode for reducing conversion delay on priority channels. And advanced result handling capability also it provides, like you can select result width of 8, 10 or even 12 bits, fast comparison mode for quick threshold check, and independent result registers. I hope you now have a clear understanding of the basic concept of VADC. For more details explanation, feel free to check out the previous video where I covered it in depth. Now let's move on and see how we can configure an analog channels and read sensor data. To understand the ADC functionality, let's take this example. Here we have connected the potentiometer that can vary voltage from 0 to 5 volts based on the voltage level. If it is below 1.1 volts, only LED 1 will be turned on. If it is between 1.1 volt and 2.2 volts, both LED 1 and LED 2 will be on, and if it is goes above 2.2 volts, only LED 2 will be turned on. In this example, we will be working with two GPIO pins configured as digital outputs to control LEDs and one analog pin to read voltage from a potentiometer. Specifically, we are using port 0, pin 5 and 6 has digital output and AN0 as our analog input channel. What is the interesting about the AURIX TC275 microcontroller is that each pin is not limited to just one function. You can configure them for digital input, digital output, PWM, or even for other alternative features depends on your applications. To explore all available functions for each pin, be sure to check out the TC275 datasheet for detailed pin multiplexing options. When working with any microcontroller, setting up the ADC typically follows a few basic steps. Like first, enable the ADC module and peripheral clock to make sure the module is powered. And the next, configure the input pin to function as an analog input. Then set up the ADC parameters like resolution, sampling time, and choose the conversion mode, whether it's a single shot, continuous, or scan mode. After that, select the specific ADC channel you want to read from. In our examples, AN0, it is in a group 0 and channel 0. Once that is done, enable the ADC and start the conversion process. And finally, read the conversion result either by polling or using interrupt, depends on your application. Let's walk through the step-by-step process to initialize the VADC module. To enable the ADC module, we first need to activate its peripheral clock through the CLC. But since the CLC register is protected by the end unit mechanism, we can't modify it direct. So first we unlock the protected register by disabling the end unit using a special password. Then we enable the VADC module by clearing the disable bit in the CLC register. And finally, we re-enable end unit protection to lock the register back and keep the system secure. Then set ADC group 0 to normal operation mode. This activates the converter in group 0. Configure the global CFG register with the clock divider for the internal analog clock. Also initiate the startup calibration by setting up the SUCAL bit. This step is important for achieving accurate ADC conversion. And enable arbitration slot 2, which is used for background scan conversion, and enable the option to store the conversion result in the global register by setting the appropriate bit in the channel control register. And select channel 0 of group 0 as part of the background scan sequence, and configure the ADC so that a conversion result can be issued for each enabled channel, in our case only channel 0. And enable interrupts for the group 0 results by setting up the service request control register, and also assign a interrupt priority. Use the interrupt handler install function to register the interrupt service routine. Enable the result interrupt so the system can notify you once the ADC conversion is completed. Wait the startup calibration to complete. This ensures the ADC is properly calibrated before use. Finally, trigger a conversion by setting up the load event bit. This start the background scan and begin the capturing analog data. Now we understood the complete procedure how to configure the ADC. Let's check out Infineon example code. Once it enter into the core 0 main function, then it start with the initialization procedure. In our example, initially we will start with the LED configurations that we have to configure as a output mode with the push pull configuration. Then we will see the how the VADC is configured. So the initially it is the only the configuration parameters what we wanted to configure. For example, like how much frequency we want, then what is the resolution. It supports 8 bit, 10 bits and 12 bits. So here we are configuring with the 12 bit, and the sample time, and also the whether we wanted to go with the internal supply, and also internal supply with the 3.3 or 5 volts, but currently we are going with the 5 volts. And if you wanted to give externally, even you can configure by giving the reference voltage and configure the reference voltage also. The actual installation will start here. If you see, if you remember, the first step is to enabling the ADC module and also the clock. So if you see, this is the register where we wanted to enable the clock for the ADC. Let us check here the register. Okay, so this is the CLC registers. So what we are loading it, we are loading with all bits as 00. It means that, so mainly we are focusing here, this is to enable the module. So as we remember, this is a protected registers, so that is the reason we are providing the password to unlock the register, and we are writing our data, and again we are locking the register. Then we need to configure whether we wanted to go with the 3.3 or 5. So what will be the my voltage? So configuration parameter is 5 volts. We wanted to set it as a 5 volts. We will configure which ADC group, and in that particular group what is the channel. Let's see which channel we have configured. So in our case we have configured channel 0. So if we say this is a channel 0, so this is how the configuration will happen. So suppose if you want to learn like complete more details, what are the registers we have in the VADC, and also what are the configuration parameters, you can check it out here. If we see, like, these are the registers which is involved for the VADC configurations, so you can go to each individual registers to understand deeper into it. And also, as I explained earlier, the overall procedure to configure VADC, these are the steps we follow. So we just seen like 2 to 3 steps now. So similarly other steps also follows, and the same way the implementation also taken place in this code. And the final thing is, whenever we wanted to read the ADC values, we'll get it from the result registers, because this is a background scan. So for automatically for every event the ADC read will happen at the background, and the result will be stored in the resultant registers. So you can go through this code and also the data sheet, and also you can refer the each registers. Still, if you have any queries, or you wanted to learn more or to know more, or have some particularly some questions related to the VDC, you can add in a comment section, we will answer back. Finally we move to the demo now. So here the default voltage is 0 volts, which is less than 1.1 volts. So LED 1 is turned on. We will change the potentiometer. So basically we increase the voltage. So now we'll see both LED 1 and 2 will be turned on, because it is between 1.1 and 2.2. And then again if we increase, so only LED 2 is turned on because it is above 2.2 volts. Now we just change the potentiometer. Will increase from 0 to 5 and 5 to 0. Just observe in the graph of the terminal. Thank you for watching. If you like the video, please like, share and subscribe.